Yeah, exactly. Looks okay on Zoom. Yeah. Maybe. Okay. So we have the last talk of the morning before the coffee. It's going to be Sahl. He's going to talk about leading and trailing spiral arms in a nearly broken disk. And I will let you know 3 minutes before the end. Correct?
Yeah. So to give some context, some observations in some of the brightest disks, we can see a variety of substructures which all have their many explanations. A common one for the rings and gaps, for example, are through plan disk interactions. For some of the large-scale sparse structures, one explanation could be a gravitational instability. And on top of these, when we also look at some scattered light observations, we can also see shadows in these disks along with spiral structures and rings. The origin of these shadows is a misaligned inner disk that casts a shadow on the outer disk, and a schematic diagram is showing the orientation disk is shown here. And one way you can get the inner disk a misaligned, for example, is through a flyby, and I'm interested in these in the shadows. Is the interest comes from a previous work where the shadow structure was prescribed onto the temperatures as azimuthal dips. So you can see two narrow-lane shadows where in the shadow region the temperature is lower, and these shadows can also create their own spirals in the density structure. However, in those simulations, the hydrodynamics of the inner disk was not modeled, and in simulations like Beck's, where the hydrodynamics of the inner disk was modeled along with using live radiative transfer, so you can model both the inner disk and the shadows cast by the inner disk consistently. The sparse structures, the shadows were not seen. However, the disk's setup was quite different to previous work, so it's difficult to make a direct comparison. So that's going to be the focus of this work, where I look at misaligned circumbinary disks. And so the initial disk setup is quite simple. We just have a normal disk around 2.5 solar mass stars, where the orbital plane of the binary is inclined by 45 degrees relative to the disk. And we use a 0.2 solar mass disk. And given the high disk mass and the temperature effects of the shadows, we don't include self-gravity and we use an isothermal equation state, even though they're both important. The main reason is it allows for an easy understanding of what the inner disk is doing, what effect the inner disk has on the structure on the structure of the disk. And we don't have to worry about shadowing effects or gravitational instabilities for now. So what actually happens? This video shows the evolution of the disk, and since the binary is misaligned, it creates a warp in the disk, which eventually breaks, and you see the formation of leading spiral arms, which I'm not sure how easy it is to see on the screen, but on YouTube it should be quite visible. The main thing about these spirals compared to spirals like gravitational instability is that these spirals do not rotate with the disk, and they're pointing in the opposite direction as expected. So instead of a clearing spiral arms, they are leading instead. To understand why we had a look at what the inner disk is actually doing as the simulation evolves, and the top panel here is a particle plot of the density, and the bottom panel is a cross-section slice of the density. So when the disk is misaligned and we can see the leading spiral arms, the inner and outer disk are not completely broken. They're still connected at two nodes, and it is from these two nodes where the leading spiral arms are launched. At a different time where the inner and outer disk are more cleanly separated, the two connecting nodes are not really there anymore, and we don't see the leading spirals either. At a later time, when the disk is mostly aligned, once again, the two connecting nodes are not there, and leading spirals also begin to vanish as the disk becomes more and more into alignment. We also had a look at the velocity structure to ensure that the spirals were not an effect of the viewing angles. And if we first look at just the misaligned case, we can see that in the radial velocities, we see two leading spiral arms, which coincide exactly with the location of the spirals in the density structure. And in the other two panels, when the connecting nodes don't exist, we don't really see the spiral structures in the velocity structure anymore. When this is broken, there's next to none, and as the disk is aligning, these spirals in velocity are getting weaker and weaker and less defined. So to see the evolution, to see how the inner disk evolves over the entire simulation and to see its effect, we plotted the radiative disk misalignment, which is defined as given here. And the only thing we need for that is to define what is the inner and outer disk. And the boundary of the inner outer disk is defined by the location of the gap. So that's the inner disk, and that's the outer disk. And the actual location will change over time as the gap location also evolves. So at this, in the snapshot, where you can see the spirals, the relative this misalignment is about 20 to 30 degrees. And the key things to note when I start playing the video is what happens at high relative this misalignment, so about 40 degrees plus, and what happens at low relative this misalignments. So as it reaches the phase where it has a high relative misalignment, the spirals are quite weak, and as it decreases and reaches the more optimal range of misalignments, this is when the leading spirals are at the strongest. And as the disk evolves, the inner and outer disk become more in alignment, and you should see that the leading spirals are becoming weaker and weaker, and eventually the spirals are not there anymore, and just a disk with a shallow gap. And so now that we have a decent understanding, I use that term loosely, of when the spirals are forming, we included the additional physics, which are quite important for this for the disk setup here. So even with including both live radiative transfer and self-gravity, the formation of the leading spirals is quite consistent across all simulations. It's mainly the relative disk misalignment that is important. So for next part, we also look at a lower disk mass, or for most people in this room, a high disk mass. So it's still a 0.02 solar mass disk. And everything else is the same, except now we start with including live radiative transfer. So an important difference you can immediately notice is that the structure is a bit more complicated than the high mass disk, where you seem to have both leading and clearing spiral arms that exist at the same time. The other thing you'll notice is that the color scheme has changed, and that's because instead of the Stockman density, to make it easier to see the spirals, I have divided the surface density by an asymmetrically average profile to see the spirals more cleanly. And so you can see as the disk evolves, at some points it has just leading spiral arms, it switches to a trailing spiral arm, and this cycle of leading and trailing spiral arms will repeat a couple of times. And while you're switching between the two, you can have phases where you have both leading and trailing spiral arms at the same time. So I think on the switch is coming up. If you did miss the switch, the video will appear again in the latest slide. I've spent too long staring at these videos. So, and eventually it ends up with just a leading spiral arms. So what's different between the low mass disk and the high mass disk? One of the differences is the effect of shadows coming to play for the low mass disk. So we now have two mechanisms for launching spiral arms. One from the interactions with the inner disk mentioned before, and now with the shadows as well. But the shadows exist for most of the simulation, and we don't see clearing spiral arms all the time. So to explain why, we can have a look at the relative disk misalignment again. So in this snapshot, the relative disk misalignment is about 45 degrees, which is just a bit, which is in the regime where the effect of the leading spiral starts to weaken, and at this point you have both leading and trailing spiral arms. So when I play the video, the main things to notice to see when the leading spiral arms form, which is at when it's below 40, and when the trailing spiral arms form when it goes above 40. So it's trailing, it goes to leading, and as the relative disk misalignment increases, it starts to switch to a trailing spiral arm again. And as it comes back down, it'll switch back to leading, and in this final cycle, it'll repeat once more. So you have leading, you get a bit of both, and it switches to trailing spiral arms, and finally back to leading spiral arms. So everything is still consistent with the high mass disk, and it's now also consistent with the previous work that included shadows but didn't include the inner disk. So yeah, to basically summarize, we get leading spiral arms due to the dynamics of the inner and outer disk when they are moderately misaligned, and we get trailing spiral arms that are due to shadows cast by a highly misaligned inner disk. Yeah, I'll just leave my summaries up there.
Okay, thank you very much. We have time for questions. More on the shy. Questions so far? Nico?
So my question is that I've not grasped or whether you have a full explanation of what's causing spiral structures when the disk is connected at the sending nodes, like the inclined disk that creates the spiral features. What's the physical mechanism there?
So,
the question is when you have a misaligned disk and what's happening at when the lines of nodes connect with both disks and what's driving the spirals.
yes, so what I think is happening is there's some angular momentum transfer at the nodes, which we show which shows up in the velocity structure. So the bottom panels are the radial velocities of the particles, and we can see that it has a positive radial velocity at that originate from the connecting nodes, which are in line with this, which match up with the spirals exactly.
I have a question myself. Do you have any promising target that we could, or an observation that where you might be seeing at the same time trailing and leading spirals? Or
I think we need to have a dedicated dust simulations first to understand whether we will see the structures in the dust as well.
Okay.
And that is learning extremely slowly. Maybe in the next phantom workshop, I can tell you what happens to the dust.
Okay.
At the moment, it's even for strokes of about 10 to the -2, it is difficult for the dust to place the leading spiral arms. But the simulations also at the moment is when the disk is at its most misaligned, so I need to wait for a few more months.
But is there any observation where we might have seen already trailing and leading spirals at the same time?
I don't think so. There were a few candidates where I saw in all the papers, they said the spirals could be either trailing or leading, but every time a future paper came and said, now that they have these rotational disk, it's a trailing spiral arm.
No question? Go on, maybe shy. I know you want the coffee, but you need to deserve the coffee. Please, one more question. Daniel? And then David.
My comment, the thing you left out, Sahl, that I think is really important to highlight is that when you discovered this, you went back to the previous literature because you're a far from the first person to simulate these circumbinary disks. And you found that in the literature, if you look really closely, this effect of the leading spirals, you can see it in previous literature. You just need to know what you're looking for, and it has been seen. And it's also, if you look closely at one of Ian Rebecca's simulations, you can also find it there. So this phenomenon that Sahl's discovered, it's been in the literature, but just nobody has looked for it the way that Sahl has. So I think it's really interesting.
I just want to make sure I understood that. So there's still no effect really from the shadow. Is that correct?
You have an effect from the shadows, which is seen for the lower mass disk, but that only happens because in the lower mass disk we have high relative disk misalignments when the inner and outer disk are nearly completely broken. So you don't have the effect that causes the leading spirals anymore, and that's where you see the effects of the shadows.
And what is that effect?
That's the trailing spiral arms that have been seen in previous works. So.
So you're saying the shadow does create, if you take away the shadow, you don't get those spiral arms.
Sorry, can you repeat
So
that?
some of those spiral arms go away if you don't take away the shadow.
Yes. So if you do it with just an isothermal disk and compare, you will only see the leading spiral arms becoming stronger and weaker depending on the disk. misalignment. So if you compare that about 7 orbits, you can see that you only get the clearance spiral arms when you include the effect of shadows.
Okay, so